Okay, let's get started. Right, I'll ask the same question that Ali started off asking. How many of you were in my talk last year about data science? Interest is growing. Okay. Right. It definitely is growing, not just in conferences, in rooms. It's growing throughout the community. This talk is titled TensorFlow. TensorFlow, what is it that you see? But it's less about TensorFlow and more about the concepts that you need in order to use TensorFlow effectively, at least to get started with, and what topics might be useful in learning, to learn deep learning. So the things we'll cover today are deep learning, neural networks, TensorFlow, and different types of neural nets. How many of you were in Ali's talk this morning? Pretty much everybody. Good retention rate. Okay, right. So before going into what deep learning is, let's just talk about what sort of problems and where deep learning can be helpful. The key areas where deep learning is being used today is where you have complex problems and lots of data. If you have small amounts of data, then traditional statistical models can work are arguably better. They can work in more understandable ways than deep learning can, and can get you to a result potentially quicker, even. Where you've got lots of data, and if you have simple problems, then simple streaming engines could take care of them. You don't need deep learning to solve simple problems. Okay. And deep learning is also useful in solving things that previously could only be done by humans, like recognizing pictures or drawing a picture, coming up with ideas, summarizing text, that sort of thing that previously we thought that only humans were capable of. A lot of these things, computers are making a lot of progress in. And that's an application area of deep learning. And the big change that we're seeing in why deep learning is becoming accessible to people is that now you've got common toolkits that are coming out, like TensorFlow, Keras, TF-Learn. Microsoft and Amazon have collaborated to create a new thing similar to TensorFlow for deep learning as well. And the idea is that you don't necessarily need to build everything from scratch. You're already given toolkits. And you can take ideas from deep learning and implement them in your existing system. They effectively democratize the process. You don't necessarily need to be an expert in an area to gain value from these systems. Right, so as Ali said, there is no real thing called deep learning. It's all just neural networks. Okay, so the model of neural networks, I won't go into too much history. Ali's done presented a very good history of neural networks and deep learning and everything. But we'll go into the effective building blocks. The notion of perceptrons kind of loosely is modeled around the idea of neurons in our brains. Or in our bodies. The idea is that you have neurons connected by synapses. Now, while that might be a starting point, it's worth noting that biological neural networks work very, very differently from artificial neural networks. There is a theory that you have simple neurons, which work kind of like we think, or rather how artificial neurons work, or perceptrons work. But there's also the grandmother cell theory, with the idea that a single neuron in our brains can actually deal with a lot more than simple inputs, outputs, and weights. So we don't actually know how our brains work fully yet. So what neural networks tend to be is it's more of a mathematical model. And we're not necessarily following the biological descriptions of things. What we're doing is we're concerned with the mathematical model of how things work. And how the mathematical model works is essentially that. You have inputs, you have weights, you do weighted sums, and you call a function on it, and that produces an output. That's essentially the building block. That's what a perceptron is. And when you're training it, what you're effectively doing is for a certain set of data, these are the weights that produce output that looks most like my input. Okay. And we take these and have more and more of these, and like Lego, put different blocks together to gain different effects. And those are the effects we're going to be talking about today. Okay. So we'll start off with a very simple problem, which is logistic regression. Okay. what logistic regression does, it's a type of classifier. You give it some inputs, you give it some training data, and the goal is that once you've trained it up, you give it some more inputs, and it will predict what class something belongs to. So for example, here, you can give it the letter A, and it will tell you whether something is A, B, or C. That's what it's learning. And the equation for this is a very simple linear equation. You have your inputs represented by X. You have your weights represented by by W. You have a bias term for B, and the output is Y. Right? I mean, most people are kind of familiar with this type of equation. It's an equation for a straight line. Okay, and right. So what we do is we take the scores from this equation. By scores, we mean Y, right? So given our inputs and our weights, we take the scores, and we run it through this particular equation. And that equation is called softmax. Okay, it's e raised to an input divided by the sums of the inputs. There's a bit of math there, but effectively what softmax does is it takes a bunch of scores and converts them into probabilities. Okay, there are many different functions that do that. Softmax does it in a continuous way, and we'll revisit that a few times today. Is that the key thing is that the way it does it, the function is not a linear function, it's a continuous function. And the benefit of having a continuous function is that you can take a derivative. And if you can take a derivative of something, you can optimize it and do gradient descent on it. That's the key thing that softmax is giving over here. Okay. So we take our inputs with our given weights or learned weights. We get scores from that equation. We run it through softmax, and that gives us probabilities. Okay. And once we've got the probabilities, does my cursor show there? Yay, good. Okay. The scores that we got from the equation, they're commonly called logits. You'll see there's a lot of jargon. People who came up with neural networks, they like jargon. They have cool names for very simple things, probably to confuse people more than anything else. What we have is we have these scores or logits. We pass them to softmax. Softmax gives us probabilities. And then linear regression is a supervised learning algorithm, which means that you have to give it a training set with pre-classified data where you know what the results are to help it learn. So what you basically do is you take your labels and run it through a cross-entropy. And the cross-entropy thing, the D function over here, is actually fairly simple. It's basically a product between your labels and the minus log, dotted by the minus log of the softmax. Now, if your label data falls under one category, let's say you're doing lateral classifications and it's A to Z, so you have 26 possible outputs, right? Only one of them will be 1. So basically what this means is the cross entropy is going to be minus log of the softmax value that corresponds to the 1. Okay. A bit of math, but the idea is that you run it through a series of processes to get to a certain value. And this cross-entropy thing is what you optimize to do your backpropagation to actually help your model learn. So based on this cross-entropy, what you're trying to do is you're trying to minimize it. Through an optimization function, when you minimize it, what that does is it changes the weights in your model. And with enough iterations, what happens is that the weights that you end up with causes the minimal amount of loss. And so when you feed it new inputs, it gives you predictions that are fairly reliable. Now, an issue with this, well, let's go through pros first. The pros of linear models is that they are extremely simple. You have 2 matrices that you're multiplying and adding another matrix. The bias is a single column matrix. W times X, W is a matrix, X is a matrix. One of the main reasons that deep learning or neural networks is gaining more and more popularity is that we now have very specialized hardware at fairly limited cost that can do matrix multiplications very easily. That's GPUs. That's basically what they do. Their sole job is basically multiplying matrices to come up with shaders or whatever. Everything is matrix multiplications there, right? So very fast GPUs means that you can do a lot of these linear multiplications and additions in very little time in parallel with using all the cores of your GPU. The other thing is a linear model is very stable. Like, you don't see fluctuations in output. It's a very kind of stable model. And the other thing is that because we're using softmax or some other continuous function, when we take derivatives, we get, the derivatives of a linear function. So the derivative of softmax is linear, but the derivative of a linear function, where'd that go? There we go, yeah. So the derivative of this is going to be a constant. And that constant is going to be basically, if you derive it with reference to x, it's basically w. Okay. And so it's a very simple model. It's very fast to compute, and you can get things done fairly quickly. Okay. Now, a problem with this is the sheer number of parameters. If this is a linear model, your x, your weights, you have n plus 1 times k parameters, right? So for y, you have k. For the bias term, you have 1. You have equal number of weights as your input, so you have n plus 1 times k. So if you think about running this on a 64 by 64 image in order to do image recognition, you have a lot of parameters. Okay? And the bigger things you train, when you're training on words, to do text processing, it gets exponentially larger. And dealing with all of that with one multiplication becomes prohibitively expensive. Okay? The other problem that we have is that linear models are linear. Well, they're expected to be linear. They're called linear models, right? But in many cases, what you have is that your output is not linearly corresponding to your input. You need some level of nonlinearity. So while things like y equals x1 plus x2 can be represented by a linear model, you can't represent things like relationships between variables. That's incredibly hard to do. So if you were to plot it or visualize the data, whenever you get any sort of data sets, the first thing you should really be doing is visualizing it to get a feel for the structure of the data. Right? If you visualize the data and you see things that are curves or wavy shapes or anything, then you know a linear model is not going to be good enough. You need some level of nonlinearity. And constraining everything to be linear probably won't solve your problems. Okay. So how do we solve these problems? And that's where I guess not necessarily deep learning comes in, but for both of these things, deep learning has today the building blocks to kind of solve these problems. The first thing we'll look at is basically a ReLU. Ali mentioned that a few times. What a ReLU is, or a reticulated unit, is it's very much like a linear function, except up until you reach a certain value, it gives you 0. Okay, just that bit of nonlinearity, just the fact that it's linear after a certain value and 0 otherwise, allows you to represent a lot of different nonlinear functions, especially when you're running it through matrices in your GPU and doing it many, many times. Okay, so ReLUs have really, really taken off and are used in many, many different neural nets. So that's one thing, and that helps us deal with nonlinearity. To deal with a number of parameters, what we do is instead of dealing with fewer layers where you have gigantic matrices, you make it go through a series of layers. And at each layer, the network gets kind of smaller but fatter. Okay, so going from a large, thin image, so for example, let's say a 256 by 256 image, which has RGB, so basically 3 parameters for every pixel, instead of that, you go to I don't know, something like a 24 by 24, but something that has, instead of 3 layers, has many more layers. Like the outputs, instead of 3 in the input system, you have 8 or 24 or 32 in the output. So as you go through the layers, the layers get smaller, they get fatter. Okay. And that's where the notion of deep learning comes from. The idea is that there are many hidden layers in your network, so the network becomes deeper. And, well, deep learning, that's why they named it, I guess. Yeah. Okay. TensorFlow, TF-Learn, these, as I said, are basic toolkits. Using them is exceedingly easy. How many of you are familiar with Python? Okay. So that's a huge difference from last year. But Python is a good language, and it's fairly easy to use. People call it executable pseudocode. But the idea is that TensorFlow, TF-Learn, Keras, these libraries, what they do is they give you a much more approachable interface. So the matrix multiplications that we were talking about, you can do it without actually having to build the building blocks yourself. So as an example, what this is doing, this is for digit recognition. So handwritten digits, it's going to tell you what it is. MNIST is a kind of well-known data set that consists of handwritten images and then corresponding labels for each of those images. So what we're doing here is that this is a kind of pre-built function in TF-Learn. You're taking the MNIST data set and you're loading the data. And one hot means that for each category, you have a separate column. So for 0, you have one column. For 1, you have another column. For 2, you have another column. For any particular image, only one of those columns is going to be 1, and everything else is going to be 0. Okay, so that's what one hot true means. The next bit of code that we have, this is basically visualizing that data. So this is what our source data looks like. It's a grayscale of some handwritten digits. Okay, I guess that's a 7. Yes, 3, yeah. But I mean, TensorFlow has nothing to do with this, right? This is just plain visualization. You're rendering the pixels using plotting functions. This is where TensorFlow is kicking in. This is how you create a model in TensorFlow. So we start off with taking our input data, or we describe our input data. And how you describe that is that you tell it what the shape is. And what this little bit is doing is that it's saying, I don't know how many rows I have, but it will have the same number of columns as my input. Okay, so that means my input can be 100 images, 1,000 images, 20 images, 5,000 images, but the number of columns is going to be the same as whatever the columns are. And the columns in that case are, location and color values. Well, actually, we don't have color values, so 0 or 1, based on whether it's black or white. The next thing we're doing is we're creating a layer. So this represents the input layer of our neural network. This represents one of the hidden layers. So we have an input layer followed by a fully connected layer. A fully connected layer is basically a layer where every single input is linked to every single output. So the output of that layer is going to depend on the output from all of the all of the outputs from the previous layer. Right. So we have one fully connected layer. We follow that up with another fully connected layer, and then we get the output, which is another fully connected layer, and then we tell it to run regression. Okay. So the network we saw previously, or the equation we saw previously, we didn't actually have to write W, X, B. We didn't have to tell it to, or we didn't have to write the softmax function to use it. We just literally told this, oh, by the way, the output is going to be fully connected. It's going to have 10 outputs. The input is going to be this one, what we got from the previous fully connected layer. And the activation function I want to use is softmax. And there are a few standard activation functions, softmax being one of them. For the hidden layers, we're saying the activation function is going to be ReLU, as in 0 up until a value, and then one, linear after that. Okay. And the loss function, the way I calculate how I get my loss is through categorical cross-entropy. There are different types of loss functions. Categorical cross-entropy simply is the cross-entropy function for categorical data. The data we have ranges from, has 10 categories, either 0, 1, 2, up till 9. So because we have categorical data, we basically tell it that. We tell it how fast we want it to learn. And we want to tell it what sort of optimizer we want to use. In this case, we want to use stochastic gradient descent. Okay. So writing the code to do this manually would be very, very time-consuming. It would take days, if not weeks. This is where these learning toolkits come in. Okay. We won't talk too much about TensorFlow, but we're assuming that if you're interested in this, what you'll do is you'll go and see how you can implement those concepts with TensorFlow. Okay, the documentation's there, toolkits are there. Instead of fully connected, you might have a different type of network there. But this is how you chain things together, where you have input data, one layer, another layer, and you're telling it how to optimize. And then it goes and does it for you. This runs on the GPU, does the calculations, and comes back to you with the results, which you can then use. Right, and the way you train the data, once you've told it how to, the definition of your model. So here we've defined the model. Here we're training it. We just call fit. And to fit, you give it your input, your output, how much of the data you want to use as your validation set, whether you want to show the metrics or not in the output, what the batch size is, what the number of epochs is. So for example, if you have a big, powerful GPU with lots of memory, then you'd use larger batches with fewer epochs. Otherwise, you'd use more epochs and smaller batches. And then you do testing. By testing, what we mean is that we test out, we hold out a bit of data from your input that we know what the output is. And then we take our model, we run it through that data, and then see how well it's performing. That's basically testing. I mean, all of these things, we don't necessarily have to understand all the details of the syntax or anything, but all of these steps are fairly common in, say, statistics, and the way you implement that against data using deep learning with Python is extremely simple. Right? Although this is Python code, this is not running in Python. Right? TensorFlow is translating this into code that runs on the GPU, and it's actually running on the GPU. So you get the performance benefit of running on the GPU, but you get the coding benefits of staying in a nice language like Python. I said Python's nice. Don't kill me. Right. So a problem that we have with neural networks is that, given enough data, they're very, very good at learning. In fact, they're so good at learning, they memorize it. The result of memorization is that it works very, very well on data it's seen before, but it does not work well on data it hasn't seen before. And when you're looking to predict something, you probably run it against data it hasn't seen before. Okay. So what we want to do is we want to limit how well it learns. We want to prevent it from learning all of our data, or tightly binding itself to all of our data. Right? And it's a common problem for all neural networks and many statistical models. Random forests, for example, have a similar problem. Any model that's very good at learning has the problem of overlearning. And we call that overfitting. So the first so solving this problem is literally called regularization. Yeah. There are a few different approaches to regularization. We'll talk about two. One is called L2 regression. What that means is that in addition to your loss, you add a term that depends on the weights of your variables. So the more weights you have, the more number of variables you have, you penalize the model. So if a model works with 2 parameters, that's fine. If a model works with 4 parameters, you penalize it more than the model that works with 2 parameters. And that means your kind of learning, machine learning thing iteratively does not go and keep on adding more and more parameters to basically completely fit your data. Because it's being penalized for adding more nonlinearity. So the more tightly it fits into your data, the less reward it gets. So at one point, it stops trying to fit your data and says, OK, this is good enough. So that's one way of preventing it from learning. And the other thing that Ali mentioned previously is dropout. And this was kind of like a surprising discovery. The guys who were doing this, they were kind of surprised by how well it worked. The idea is that from any layer to the next, what you do is when you're training, predicting, whatever, you just drop some of your output. And it turns out dropping half of your output has some very interesting results when you're trying to predict, because you take averages, and log 2 and dropping half, those things kind of correlate very well, and it makes certain things very easy. But the reason dropout works is that it forces your model to any idea that your model comes up with. It has to reinforce it across different data points. Right? So it's effectively like if you get some news from Twitter, from Facebook, and from BBC, and from CNN, you've got collaborating evidence from different places. This works in the same way. You're hiding some of the input available, and the result of that is that your model has to work harder to learn something. So if there's certain spikes in something, it can safely ignore that, assuming that was dropped during the training. Okay. And over time, dropout tends to be one of the most successful things in neural networks. Right. So now we'll talk about some different types of neural nets. The first is convolutional neural nets. Who's seen a movie where a robot or something basically just scans line by line, a robot, an image, or something. It's just everybody's seen that, right? So what they're trying to, I mean, apart from looking cool, that's kind of what they're trying to convey. So the reason for convolutional neural nets starts from the fact of, say, statistical invariance. Sounds like a weird term, but what statistical invariance merely means is that if you know the structure of your data, then you can help your model learn better by not having to learn that it needs to ignore something. So let's say your model is basically predicting letters, and it doesn't need to know the color of the letters. Now, if you go to yellow A, blue B, a blue A, or all these letters jumbled up together in your training set, if the model has to learn that it has to ignore the colors, that can be problematic. If all of your input basically has yellow A's and blue B's, the moment it sees a character as blue, it might predict that, hey, B's are blue, so I'll just output blue. So for example, taking that and making it grayscale would help in that case. That's one example of that. Another thing is, say, translation variance. If you're trying to predict pictures of cats in a photo, or detect cats in a photo, where that cat is doesn't really matter. If it's in the top left, bottom right, center, left, right, it's immaterial. However, if you just take your kind of normal big input and just tell your neural net, hey, go learn, the problem it has to distinguish the fact that a cat in the upper left is the same as a cat in the bottom left. And that's where convolutions come in. Okay, so the way these work is that they share parameters across different parts of your model. Okay, so in terms of cat example, the parameters for the cat in the top left and the cat in the bottom right are effectively going to be similar, and they're going to be shared across your network. Okay. So what is a convolution? Right. Okay. A convolution basically means it's a mini neural network. It's running on a subset of your input. So for example, if that's a whole picture, it's running on that part of the picture. And instead of having, say, 3 channels in its input for the 3 colors, it has k outputs. So it widens and lessens, kind of like neural nets themselves. But this is basically a mini neural network. Okay. And what you do is you stack them one after the other. And then you feed the end result to a classifier. When you talk about convolutional neural nets, that's pretty much all it is. Okay? And they work very well in terms of image recognition. Okay. Yeah, I'll speed up slightly. Okay, so the thing with convolutions is that you're basically taking a portion of your image and you're making strides across the image to reduce the number of total inputs you have, but you increase the depth or the, you're going from smaller, well, thinner output to thicker output, but reducing the surface area, the number of parameters. Right? And one way of reducing the size is basically jumping 2 pixels at a time, or say 4 pixels at a time. Now, the bigger your stride is, the more information you lose. So one way around that problem is to use pooling. And what pooling means is that for any convolution, instead of using the values directly, what you do is you take all the convolutions from a related neighborhood and you apply some function to it. And it could be the average function, it could be a max function, it could be a min function. If it's an average pooling. If it's max pooling, and so on and so forth. Okay. And there are different types of pooling. All of these, well, a lot of these are available in TensorFlow or TF-Learn out of the box. Ali went through AlexNet. Effectively, what you do is you have your image, you apply convolution, max pooling, convolution, max pooling, fully connected classifier. And so, like Lego, you take bits and pieces and layer them on top of each other to make your bigger network. AlexNet, I mean, if you were to write that manually in C++ to run on GPU, that would take you years. Okay. TensorFlow lets you do it fairly easily. Right. The other thing that comes out are called one-by-one convolutions. The idea is that instead of going from a certain size to a certain size, after doing that, what you do is you simply, for each of the convolutions, you have a one-by-one mini neural network. The reason for using one-by-one convolutions is that with very few parameters, you're adding another layer of neural network that gives you some level of nonlinearity and a level of learning. So one-by-one convolutions tend to work very well. The reason I mention one-by-one convolutions is that the next thing is the inception module. I mean, these guys in neural networks, you got like perceptrons, inception, and weird terminology anyway. So in an inception module, what you're doing is you're taking different models and taking their output and layering them together. And the result of this is that whatever insights that a particular model could get to, you're benefiting from having insights from all of the models using fairly few parameters. You're not increasing the parameter count or training time by much, but you're getting much better quality results. And that's why inception models tend to work really well. If you can write the code for a stack that comprises of a neural network, changing that to an inception module is basically a very additive, very small operation. It's not difficult to do at that point. The aggregation happens at this point. We're not aggregating, or we're not doing computations on this, and this to combine them. We're simply taking the output and concatenating them together. Right, recurrent neural networks. So just like convolutional networks share their parameters across different spaces of your input, say different areas of your image, different areas of your text, recurrent neural networks depend on the past. So what that means is that instead of simply having inputs, weights, and outputs, they have a third parameter that is what happened in the past. So they have a notion of memory. And where that helps is that if you're doing something like stock prediction or generating something based on what's come before, like text prediction, text summarization, that sort of thing, recurrent nets work really, really well in. Okay. Now, problem when you're taking things from history and applying them many, many times with very fast GPUs is that the learning gradients you have, they either explode and go to infinity and beyond, or they decrease to the point where the thing doesn't learn anymore. Solving the first problem is fairly easy. What we do is we basically have a max, and then we cap it at that level. We don't let it keep on growing higher than that. Solving the second problem is slightly more difficult, and this is where LSTMs come in. LSTMs are long short-term memory. So it's kind of resembles the idea that you may remember, like from your childhood, holding your dad's hand to cross the road. Okay. You don't know the context of it. You don't know when that happened, where you were going, but you might remember that particular bit of information. This works kind of in a similar way. What this looks like is that this W that's taking input and output and past thing, this W resembles a memory module in electronics. So in a memory module, what that does is it remembers either a 0 or 1, and it holds that value until it's changed. Right? And it remembers it across different iterations of your circuit. The problem with a 0 or 1 thing is that, again, we can't take derivatives. To make it derivable, or so that we can optimize, what we do is we just simply make that a continuous function. And because it's a continuous function, we can take derivatives, and we can use that to learn our parameters better. So what an LSTM is a mini neural network that has a kind of 0-1 type of thing, but instead of being a discrete function, it has a continuous function inside of it. You don't have to build your LSTMs. TF-Learn has LSTMs, as with most things. Regularization with LSTMs works. L2 regularization works. Dropout works as well if you apply it to inputs and outputs. As long as you don't apply it to your past input, then it works just the same. So how is this used? So for example, there's a lot of different uses. We'll go through some of these. But one very common thing to use in your models is this concept called beam search. So for example, if we're trying to predict what the next letter is, the quick brown fox jumps over the lazy dog or something, what we do is, as each character is being typed, we track the probability of what the next character is going to be. And what beam search does is it doesn't keep all of those predictions. It just keeps the top 2 or top 3 or top 4, mostly top 2, and it prunes the rest. So you don't have an exponential increase in memory for the combinatorial explosion that can happen through typing in random stuff. So some use cases of RNNs, text summarization. I don't know if that's viewable or not. Take my word for it. This is a very good summary of what's written over there. OK. And it is a summary. It's only 3 lines. That's a lot of text. It's a small font. Oh, well, resolutions. OK. These things can do music generation. This is actually a song composed by artificial intelligence. Or rather, the music is composed. And that follows kind of the motif of a, well, not really motif, but the style of a, what's it called, Beatles song, apparently. Although, personally, I think it's more Beach Boys, but yeah. A few years ago, the only thing these things could produce are like beeps and bops. So, yeah. Another thing you can do is script generation. So, as an example, this is a model that's been trained on episodes of Simpsons. And then we haven't told them any meaning of English or word meanings or anything. Just by analyzing Simpson episodes, it comes down to this sort of text, which may or may not make sense, but neither do the Simpsons. So, yeah. Another thing is translation. This is a model that's been given some English text and the corresponding French translations. And this is actually real node. I've got the links in the slides. But effectively, running that code and training the model, you can see losses reducing as we go down, 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 down. OK, right. And then finally, at the end, we give it some words where say he saw a old yellow truck, and it translates into something. I don't know if this is correct or not. Does anybody know French? Is that relatively correct? OK, cool. There you go. It does a better job of translating than I do. OK, autoencoders. This is another use of recurrent neural networks. This is actually taking images with low resolution and upscaling that to 4K. This is a website, Let's Enhance. You can actually literally go there, upload your blurry image, and it will give you a sharper image. It hallucinates the detail in the image based on patterns. And that's quite impressive, and it works. I've tried it a few times. Style transfer. You have a picture, you have a style, and you can apply those together. You've seen these on the internet. These are not actually too difficult to implement yourself. Yeah. So if you have a cabbage and another cabbage, and you want to... Oh, sorry, if you have Donald Trump in here. Right. Right. But nearly there. So generative adversarial networks, this is one of the most exciting areas in neural networks in decades, I'd say. Yeah. The idea is that you have a generative network that is trying to generate some data based on its own model, and you have a separate network that's trying to detect whether this data is real or fake. So let's say you're trying to detect fake news. This guy is trying to detect fake news, and this guy is trying to generate fake news. Our detectors aren't working very well. But they're effectively in competition. So this guy throws something at the discriminator, and the discriminator says, yes, this looks real, or no, this doesn't look real. Over time, with enough iterations, what happens is that the generated data distribution looks exactly like the real data distribution. And that can give you some pretty impressive results. So for example, StackGAN is a model where you can give it a textual description of something, and it will generate an image. So this thing where it says, this small bird has a white breast, light gray head, and black wings and tail, it's not doing an image search. It's generating a picture, or generating 3 pictures based on that description. And those birds look pretty real. Okay? It's not selecting from an existing pool of images. It's generating that. Okay? I can't draw a bird like that. Pix-to-pix is a common thing. Made some waves last year, where you basically draw some shapes, and it translates it into photorealistic images. It draws from an existing pool of images. Training models. Apple are actually using this. The way this works is that you've given faces and cartoons. You just haven't told them that these faces belong to these cartoons. And once this has been trained, you can give it any face, and it can generate that. Okay. CycleGAN. I think this was MIT that did this. They basically gave it a video of a horse and pictures of horses and zebras, and it basically made a video of zebras. That looks like a zebra. This is on YouTube. This is pretty impressive, right? Without any sort of context, it made a video of zebras. Simulated training sets. Sorry, Apple didn't use that. Apple uses this. What this does is that when you're doing eye recognition, getting enough input data, people looking this way, that way, that way, that way is quite difficult. So you train a model to generate eyes looking in different directions. And so you can train your algorithms based on the output images of a generator that's been trained using a GAN. Imitation learning tries to mimic what humans do. They're used in, it doesn't have to be visual. They're used in particle accelerators. So instead of running full multi-color simulations, they can basically tell you that this is the distribution where where a particle might actually be in, based on GANs. Captures, or rather beating captures. At one point, it solves captures to a point where it resembles humans. They're getting better and better at solving captures. This was one of our, a lot of the content that I'm presenting are based on Udacity courses, or rather one Udacity course on deep learning. The content is freely available, but the face generation is that we gave it a bunch of faces, like a few thousand faces. We didn't tell it that these were faces or humans or anything else. We trained the model, and the final output was basically faces it generated. These are faces that a 10-line algorithm running on a GPU based on input data basically generated, right? I mean, some of them are not necessarily good. That doesn't look very much like a face, okay? But some of these are pretty impressive. That could be a face. I mean, the images were pixelated, so there's that, there's that. So, I mean, this is where GANs are basically shining, kind of mimicking humans in various scenarios. Tools, you have TensorFlow, TF-Learn, Keras, Microsoft and Amazon have collaborated on a new one. Lots of stuff out there. It's a great time to get started in this space. One other tool is TensorBoard. And TensorBoard is incredibly useful. A big problem of neural networks is that you can't understand what's going on. What this lets you do is basically see the parameters flowing through your layers of your network and how optimization is working and which bit is doing what. Okay. It's still not as good as, say, a random forest or something telling you that this is the reason why I have categorized this into this category. It won't tell you that, but it will. If you're seeing that your network isn't learning in certain areas, it will help you in identifying issues. Implications, rise of the machines, probably. More likely, Uber having automated cars and kicking people out of jobs. That's one thing. Although in certain areas, it might be doing things that humans do repetitively, monotonously, where the major value may not be in, and it may relieve humans to do other things, so digital assistance rather than digital replacement. One really interesting area was where they did in the States for Little League, where if somebody kept track of the scores and basically fed it into a neural network, it generated a news report. Like little Bobby scores a home run or something, and it actually generated a kind of news report that looked very much like a formal article on a sports website. So this can be applied to do things that are currently not being done, not necessarily replacing humans and doing what they do. Anyhow, well, that's for the talk. And if you're interested in this sort of thing, in deep learning, there's lots of free resources available. Udacity's deep learning material is very good. They're paid courses, but they're free content as well. Sebastian Sroon, he's the founder of Udacity. He's put a lot of all the video lectures on the Udacity deep learning stuff. There are a few different courses now, are available on YouTube free of cost. Siraj Doval has a whole kind of religious cult around deep learning. Andrew Ng, or I think it's pronouncing, but it could be NG. He's got a new initiative with deeplearning.ai. It's a Coursera course plus a website. It's looking really, really good. There's also a deeplearningbook.org that covers a lot of the base material. But a lot of universities, MIT, Oxford, there's been a lot of research on text mining, on lots of other things that take advantage of deep learning. So if you're interested in those things, great time to get started. It's just picking up. Anyway, thanks for coming.